We started in space, talking about energy leaving the sun and striking the Earth's surface. Then we moved into the atmosphere. We talked about how the atmosphere interacted with that incoming radiation. Then on to the ocean basins to talk about circulation of the oceans, how movement of the oceans, movement of the atmosphere balances out the disproportionate energy input to the Earth system. Now we're going to go below the oceans, below the land surface, and talk about the solid Earth and how the solid Earth itself is circulating. When we look at the Earth, it's seen here as a series of spheres, pocketed spheres like a Russian nesting doll. We start with the surface. The very surface of the Earth is what we're most familiar with. The center of the Earth, located right about here, is about 6,400 kilometers below us. The deepest well ever drilled is the Kola Super Deep Borehole, about 12.2 kilometers deep. That's around 40,200 feet or so in English and American. So just a very tiny poke into the surface of the Earth is as far as we've got in terms of technology. Most of what we know about the Earth's interior comes from seismic waves, as we'll see over the next lecture or so. It's heat inside the Earth, decay of nuclear materials, and the heat that's generated by those nuclear materials and their decay that drives the Earth's movement, the Earth's circulation, the geodynamo, and the mantle convection of the Earth. Again, the Earth's interior is explored largely from seismic information, the behavior of those seismic waves as they move through the body of the Earth, the changing speed of those waves predominantly. Starting out with primary waves, or P waves, we can see the ground is shaking in this orientation, back and forth. So if you're standing on the surface and this seismic wave, this P wave or primary wave passes beneath you, you would shake from side to side. And that's similar to the compression induced on a spring, say a slinky. You force it with your hand and that wave is going to travel down the length of the spring in this direction. Alternatively, we can have what's known as an S wave or secondary wave. And this wave moves vertically and transversely. So back and forth in this orientation, up and down in this orientation. Whereas this P wave is moving back and forth only along this axis. So we can think of the S wave as taking a string and flipping that string, or a rope, flipping that rope. Garden hose, if you prefer a garden hose. You induce a wave in that structure. So here we're going to take a string, we're going to wiggle it up and down. That's going to produce a wave. That wave is going to travel in this direction from left to right. And the movement is going to be up and down, vertically or transversely if we were to shake it from side to side. So different than compression wave. You can think about a compression wave as slapping the surface of a desk, a table, dropping a rock on the floor. That compression wave is going to travel through that floor away from the initial compression point. S waves are going to result in a movement or a translation of material, whereas P waves don't. It's just a compressional wave traveling through. There's movement here. As a result, we often see more damage associated with these types of waves than these types of waves, because the ground is actually moving. Structures are being deformed and stretched and twisted and mangled, ultimately falling, perhaps. So these are our basic types of waves, the two waves that are most important for us in elucidating the interior structure of the Earth. So again, we have compressional waves, or P waves, and shear waves, also known as S waves or secondary waves. Now, when we plot an epicenter, epi means on top of. Epidermis is your top layer of skin. Your mesoderm is the middle layer of skin, for instance. So the epicenter is going to represent a point on the top of the Earth's surface, or at the Earth's surface, where an earthquake originates, or any other large seismic activity, a nuclear weapon, for instance. Very large stockpile of fertilizer is going to induce this type of wave at an epicenter in those instances. An earthquake will be below the surface by some amount. If it's below the surface, say located right here, that's known as the focus. The focus is where the Earth movement actually occurs. The epicenter is the point on the Earth's surface above that focus. So the focus here, epicenter here. As waves travel from that focus through the Earth's body, they're going to be reflected and refracted potentially. Initially, this wave is going to travel a great distance, both the S waves and the P waves, up to 105 degrees away from the epicenter. We will see S waves and P waves intercept the surface and be picked up on a seismograph by scientists, or at least a robotic seismograph in some location. And that's going to tell us about the material that this series of waves travels through, because the speed of the wave is going to be proportional to the material, the density, the rigidity of the material. And the net result is we're going to have these waves appear at the surface to 105 degrees. Then there's what's known as a P wave shadow zone, where we have no P waves reaching the surface. It says here, no direct P waves. That's because some other odd things can happen when waves bounce through or into changing densities of materials. So for our purposes, no P waves in this shadow zone. Subsequently, at 140 degrees, they reappear. We'll see P waves on the opposite side of the Earth from the epicenter at 140 degrees to 140 degrees, and we'll see P waves and S waves from 0 to 105 degrees, 0 to 105 degrees in this depiction. Now, the reason this happens is the waves are traveling through different materials. So we're traveling through rigid material here at the surface. The lithosphere is the rigid portion of the Earth, the solid portion of the Earth. Below that, the Earth becomes more and more plastic. The deeper we go, the more plastic it becomes, the more manipulatable, the more formable or deformable it becomes. That changes the behavior of the waves, such that if a P wave is to strike the liquid outer core, it's going to be refracted into that denser material, travel through that material, be refracted again when it reaches the boundary of the outer core and the mantle, and then continue on to appear at the surface here. Any wave striking in between here and here is going to be refracted away such that it doesn't appear at the surface. If it's more direct, the wave is going to travel through the mantle, hit the outer core, be refracted again when it enters the solid inner core, and refracted again when it reaches the liquid outer core, ultimately being refracted by the boundary with the mantle and reaching the surface here on the opposite end of the Earth. Now, S waves can't travel through a liquid at all because they're transverse waves. They can't move that material back and forth or up and down. So there's no passage of S waves once a liquid boundary is encountered. So we can have wave bending. The waves curve as they travel through materials that change in their characteristics. We have the shadow zones appearing here, both the P and S wave shadow zones. And we can see that illustrated here in a pretty similar way. Again, we'll start with P waves here. The focus is located somewhere just below the epicenter here, generating earthquakes that are going to travel away in all directions from that focus. If they run into a liquid boundary, they may be refracted into that liquid or reflected off of that liquid. The net result is the appearance of the shadow zone, the P wave shadow zone. The difference here, S waves don't travel through liquid at all. So they encounter a liquid, they stop. And as a result, the S wave shadow zone goes from 105 degrees away from the focus to 105 degrees away from the focus on the opposite side of the Earth. So the P wave shadow zone is going to be a band, fairly broad band, but still a band of shadow here and a band of shadow here, where alternatively the S wave shadow zone is nearly half of the Earth. And just a diagram illustrating the potential complexity of waves as they bounce through different materials traveling through the Earth. And another one here. As observed on a seismograph, we're going to see something like this. The primary waves because they're primary. They appear first. The first appearance of a wave is going to give you a pretty strong hint on the size of the earthquake. Ultimately, we're going to have secondary primary waves, you might say, the PP waves, followed by secondary waves, or S waves here, which are called secondary waves because they appear after the primary waves. Primary wave, secondary wave, and then last but not least, the surface waves. These surface waves are what are going to generate most of the dramatic video footage of earthquakes. The shaking of buildings, wine bottles falling off of shelves, dogs going crazy, sidewalks spouting water, things like that are generated by surface waves predominantly. They can be generated by the S waves and P waves as well, but you get a different kind of drama from those. Why does this happen? Well, it happens because the Earth isn't uniform. It's not homogeneous from the surface to the core. There's a variety of materials encountered along the way and a variety of physical states as well. Whether it's a solid, a liquid, or a gas is going to be important. How dense that solid, liquid, or gas is will also be important. So starting with the surface, looking at wave speeds here in kilometers per second, we'll begin with the P wave. P waves are going to be the fastest. That's why they appear first. They start out at around 5 to 6 kilometers per second here at the surface. Travel through the lithosphere at a high rate of speed, and then they slow down a little bit. They slow down right here at this boundary, which is the boundary between the lithosphere and the asthenosphere. Asthene means weak. This means rock. So the rock sphere is underlain by the weak sphere. This means it's ductile, it's plastic, it's oozable, it's more toothpastey than the crust itself, the soft bit of dough beneath the hard crust of a sourdough bread. Now, gradually, as we get through the asthenosphere, the density is continuing to increase. The density increases to a point where the wave speeds up dramatically. And this point here, where the wave speeds up dramatically, is a critical point in the Earth's structure. This is the boundary between the mantle, in particular the upper mantle, and the lower asthenosphere. So this abrupt increase in wave speed marks the boundary between the asthenosphere and the mantle. Subsequently, traveling into the upper mantle, we hit another boundary where the wave speeds up again, and this is the boundary between the upper mantle and the lower mantle. Okay, so the speed of the wave is going to be dictated by the material density and the material physical state that a wave travels through. Subsequently, the mantle is comparatively uniform, and there'll be a gradual increase in speed all the way down to the Earth's outer core, where we go from this ductile plastic material to liquid material, but a liquid material with a much greater density. So that's a bit of a monkey wrench in the works there. That's depicted clearly when we look at the density profile here. So the density jukes and moves with changing materials. The big jumps are going to be at the boundary between major interior structures of the Earth, which is how we define the interior structures of the Earth, so no surprise there. We'll see a jump in density at the asthenosphere mantle boundary, another jump in density at the upper and lower mantle boundary, fairly uniform increase in density until we hit the liquid core. We change phase from plastic to liquid, but our density goes way up. And because the density goes way up, the speed is going to increase. Then speed is going to increase more gradually until we reach the inner core. And now we're going back into a solid, but a solid with a very high density. So there's going to be another jump in speed. So the density is going to dictate pretty much entirely the P wave behavior here. S waves, it's going to be density that can be completely overridden by the physical state. So here, the density is increasing just as it does with the P waves, but once we hit liquid, no more S waves. That's that. Now they can appear again in the Earth's inner core, which is solid, which seems a bit mysterious, except the source of this energy that's generating this S wave that suddenly appears in the inner core, surrounded by liquid, which it can't travel through, is a P wave. The P waves travel through the liquid, they strike the inner core, and they generate an altered P wave, and they also generate a new S wave. So using this, we can model the Earth's layers. We can break it into the crust and lithosphere, the rigid outermost portion of the Earth. We travel further down into the Earth, we get some partial melting. This generates the asthenosphere. Below the asthenosphere, we have the mantle that has an internal phase change at 400 kilometers, located right here. This is the boundary between the upper mantle and the lower mantle. We have the core mantle boundary, where we go from plastic to liquid. Then we have the inner outer core boundary here, where we go from liquid, high density, mostly iron and nickel, to even higher density, solid iron and nickel, predominantly in the inner core. Now, the little bits of extra ingredients here in the outer core and the inner core are very, very important in determining the behavior of the geodynamo, the generation of the Earth's magnetic field. Looking at a cross-section expanded here, we can get maybe a clearer vision of what's going on. So we see a rapid increase in wave speed right at the surface where the crust is rigid. We see a transition to lower speed here at the bottom of the lithosphere that's related to the beginning of the phase change, partial melting, as we go into the asthenosphere, the weak sphere. So we have a low velocity zone here because part of this material is molten or melted. It's a liquid of some type, very dense liquid. As we move back into the solid portion of the mantle, into solid peridotite, we'll see again a gradual increase in wave speed, phase change within the upper mantle. You'll see a shimmy, a juke, a move here to slightly higher speed in terms of wave velocity that is going to be related to that change in phase here. And that's going to be followed by another phase change here from the upper mantle to the lower mantle. This was noticed about 100 years ago by this man. This is Andrija Mohorovičić. And this discontinuity here, the Mohorovičić discontinuity, is the boundary between the crust and the mantle. And this is where the seismic velocity increases by about 1 kilometer per second. So he noticed this 100 years ago from looking at seismic data about an earthquake that occurred, I think it's about 200 miles south of Zagreb in Croatia, something like that, south of Zagreb. So he noticed this change in wave speed that he attributed to a change in density, and he was correct. So this Mohorovičić discontinuity is more commonly called the Moho. For people that don't speak Serbo-Croat, Moho is easier than Mohorovičić. The crust averages thickness of about 7 kilometers in the ocean basins, about 33 kilometers in the continental crust, and it can be substantially thicker than that in some locations. Now, your book will say something to the effect of 70 kilometers under high mountains. It's actually more like 200 kilometers thick underneath the Tibetan Plateau. And there's a reason for that, a physical reason. It's kind of like a margarita of rock, where we have chunks of rock mixed in with some liquid, and that is 200 kilometers thick. So it's not quite rock, it's not quite crust, but it sure looks like it. We see this Mohorovičić discontinuity located here. Again, this is where we see a slight increase in density. This increase in density is abrupt. It takes place over a depth of about 500 meters is the estimate. That is nothing when considering the bulk of the Earth. And this brings us to isostasy. It's also known as a buoyancy force, or the buoyancy force that pushes a low-density continent upward, or a low-density ice cube upward, or here in this famous fake iceberg picture, the lower density of the ice relative to water. Ice takes up slightly more space, about 10% more space than an equivalent mass of water, so it floats. When we see a big iceberg out at sea, you're only looking at about 10% of the volume of that iceberg. Now, it's not like a giant icicle floating in the ocean as is depicted most often. In fact, even here, this would not float like this. This would flip over on its side or even go upside down. This is the most unstable possible position for this. This force is known as isostasy. This is the reason continents are usually above sea level, not always, but usually, and ocean crust is below sea level, not always, but usually. And again, this goes back to Archimedes taking his bath. There's some debate whether that actually happened or not, but it's a good story. So we'll say it goes back to Archimedes and his bath. Now, starting with the lithosphere, again, usually about 100 kilometers thick, can be as thick as 200 kilometers. Again, it's thickest under the Tibetan Plateau. At the base of the lithosphere, there's some partial melting, and this, again, causes the decrease in the velocity of the S waves.